Hello everyone. Today's topic is about finite state machine or FSM. I've already covered FSM in details in two of my videos, verilog video, and those videos are available on verilog playlist. And I have also provided the link for those videos on video description section. And the lecture number is 39 and 40. Okay, so if you have not watched till now, then please first watch these videos, this lecture number 39 and 40, to understand the basics of Mealy machine and Moore machine, as well as the basics of finite state machine. Okay, so today we are going to learn more about this finite state machine. As we know that finite state machines are two types. One is Mealy and another is Moore. In Mealy, what happens? The output depends on the input and the state. Here the input means not the input to a flip-flop. Okay, here input means some external input to a machine. And what is this state? In many books, in mostly the digital books, they write state in a finite state machine. State means actually the output of a flip-flop. That you have to remember always. This state means it is the output of a flip-flop. So this is my D flip-flop. So this is my input and this is the output, right? Now I have written here A. So this is the output of a flip-flop. Whatever is the output of a flip-flop is called state in finite state machine. Okay, and what is this input? This input is not this input to this flip-flop. This input is some external input. It is coming from the outside world. Okay, and here it is output depends on. Here output doesn't mean it is the output of a flip-flop. Output means the output of a FSM, finite state machine. Output of a flip-flop and output of FSM are two different things. Okay, so this output of a flip-flop is fed to, let's say, another circuit. Then we get the output, and it is, this output is called output. This here it is written output depends on input. So this output is the output of this finite state machine, and this output interacts with the outside world, and this input is coming from the external world. Okay, so this Mealy machine looks like this, and this Moore machine looks like this. Okay, so inside the circle, you will have sometime the letter or sometime some digital number like 0 or sometime 00 or 000001. Okay, and this if it is a letter, then these letters are called state variables. Okay, state variables are again nothing but, see, state means output of a flip-flop. State variables means it is representing the output of this flip-flop. A means now it is the output of a flip-flop. Okay, so these are the state variables. So here inside the circle it is state variables. Okay, then there will be a arrow mark. Okay, this arrow is called next state. Okay, from where it starts it is called present state, and where it goes to is called next state. And then if it is Mealy, then it will be written something called 0/1 or 1/0. The left side is called input, this input, and the right side is called output. Okay, and this arrow mark, what does it mean? That means when your FSM is in state A, that is present state, this is called present state A, and when input 0 comes, this 0 comes, the input comes, then it will move to next state. It will move to next state when input equal to 0. Okay, when it is at present state, then it will move to next state when input comes, and here is the input, and that time your output of the FSM will be 1. Okay, so when it is in some state, present state, it will move to next state when input comes, and it will give a output. Okay, and this one is Moore machine. Okay, and the representation of Moore machine is like this. There will be state variables. Again, it can be 0, it can be like this 00, or it can be 000 or 1. Okay, but here it is written state variables, and state variables nothing but output of a flip-flop. Okay, then this division sign, then some 0 or 1, okay, and this 0 or 1 is called output of FSM. Here it is 0/1 or 1/0. These right sides are called right sides, represents the output. Here this down part, it is output of FSM, and this arrow mark is anyhow it is next state. So when FSM is in this state, it will move to next state when input equal to 1, and this is the input. There is no output is here, okay, and this is input. So this is how this Mealy and Moore machine representation is, okay, looks like. See here, if we see this verilog code, the parameter s0 equal to 0, s1 equal to 1. This s0, s1 are called state variables. Here I have mentioned here, right, state variables, output of flip-flop. So these are the state variables, okay. The next one, let's analyze this one, okay. So this is a Mealy machine, right? So here, if FSM, the first one, if FSM is in this state, that is 0 0 or AB. See here, AB, initially we had single letter A, here also single letter A. Now we have double two letters, right, A and B. Then A is 0 and B is 0. Here A is 1, B is 0. Here A is 0, B is 1. See, we already learned this. These are output of a flip-flop, right? A is output of a flip-flop. This is state variables. Again here it is written B. Then again it is a state variables. So that means 0 0 means here we have two number of flip-flop. Okay. This A is for one flip-flop. A, it is one flip-flop, output of one flip-flop. B is output of another flip-flop. So here we are using two number of flip-flop to represent this for this Mealy machine. Okay. So when we are in state AB, that means 0 0, and if input comes, here input 0 comes. If input comes, input equal to 0, then it stays in the same state. See, it stays in the same state. Okay, and the output of FSM equal to 0. Output of FSM equal to 0. If input equal to 1, input equal to 1, then it will move to next state. And next state is AB, that is 1 0. Next to move state, and it will move to next state only when the clock pulse arrives. That you have to remember, okay. And the output of FSM equal to 1, and output of FSM equal to 1, and this FSM equal to 1, and it will move to 1 0 only when the state equal to 0 0. See, because output is function of input and present state. That's why I have written here this line. It will move to next state 1 0. So that is the output, okay. You will get output, okay. Output is function of, in Mealy, output is function of input. So it will move to next state 1 0 only when input equal to 1 and only when it is in state 0 0. And because this is what I call, this is how to analyze this one, okay. This line, output is function of input and state, okay. Next one is now the present state is 1 0, right? Now present state is 1 0. Now FSM is in 1 0 state. Here the output of FSM remains 1 until see. Then what happen if it is in state 1 0 and 1 comes, then output equal to 1, right? So the output of FSM remains 1. So here output of FSM remains 1 until input equal to 1. Sorry, it is not input equal to 1, okay. This is input equal to, it should be input equal to 0, okay. So it will remain in state 1, sorry, it will the output of FSM remains 1, means this one, until input equal to 0, because when it is in state AB 1 0 and input 1 comes, then it gives output. But when input 0 comes, until the input equal to 0, it will give, this state will give the output 1. This line means, okay. So in this state here, in this state means here it is in state AB 1 0, and if input equal to 0 means this one. Sorry, this one, okay. So when it is in state and this 0 comes, then what will happen? Then output changes to 0. Then output changes to, before that the output equal to 1 when input equal to 1. But when input comes and the state is AB, then the output of FSM is 0. And see what I have written here, it will move to next state 1 0 only when the clock pulse arrives. But here it is not depending on the clock pulse. Here this line, in this state if input equal to 0, then output changes to 0 at that time. It is not synchronized to clock signal. Okay, see, this Mealy machine, one disadvantage is that sometime it is not synchronized to clock signal. See, in this case it will move to next state when input comes and output will be 1 when clock pulse arrives. This line. Okay, but in this case what is happening? Even if there is no clock signal and if input comes suddenly here, then it is giving output. This is one big disadvantage of this Mealy machine. So in Mealy machine, output change, because we know that output depends on the input or present state. That means output is function of both input change and the state change. Even if the input changes and if state is not changing, then also we get the output here. So this is what is happening here. So in Mealy, output change when input change as well as when state change. And because of this reason, what happens? So a false output may occur between, a false output may occur between the time the state change and the time input is changed to new value. So see, let's say in this case, let's say this input 1 comes, okay, input 1 comes and it is changing to, that means it is moving towards next state. In between, let's say suddenly, what happens? 0 comes. Then what will happen? 0 comes, then also it is giving one output, FSM output, and it is moving to next state. And here the next state is same state. So definitely our next state should be this one. But in case if 0 comes, because it is not depending on the clock, then we have another next state and it is the same state. So possibility is there that it may generate a false hardware. So a false output may occur between the time the state change and the time the input is changed to a new value. Okay, but in case of Moore, it doesn't happen. See, in Moore, this is input, there is no there is no output here, right? Here output changes only when state changes. The output doesn't depend on the input here. This is another advantage of this Moore machine. See here, input changes, then it will move to next state. Input changes, then it moves to next state. Okay, input changes, then it will move to next state, and the next state is this one itself. So here it always works with respect to the clock. That means it is synchronized with the clock. So possibility is there that it is not going to generate a false hardware like the Mealy machine did here. Okay, let's analyze this one. Okay, this is a state table. Okay, this is a present state and this is my input and this is my see, state here means the output here. Okay, state, always remember, state means the output of a flip-flop. Input is coming from external world. Next state means again output of a flip-flop. Okay, so here present state, AT and BT. So A is state variables, B also state variables. So two state variables means there should be two flip-flop. So we should use two flip-flop for this one. See here, one flip-flop, then another flip-flop. Here the state variable is A. So that this one is A, then this one is A bar, this one is B, then this one is B bar. Okay. And what is AT, BT? Then AT plus 1, BT plus 1. See, current state is at time t. If current state is at time t and next state is t plus 1. If this is the current state, the next state will be, so t plus 1 here means it is representing the next state. Okay, and total 2 number of flip flop required because 2 state variables we have taken here. Okay, and these A and B are state variables, and these are the physical flip flop output. Okay, already I explained. And this is my this finite state machine diagram, and this is the truth table or state table for this diagram. Okay, sorry, this finite state machine. And here AT plus 1 and BT plus 1. See, AT plus 1 and BT plus 1. This is function. This it is a function of this AT plus 1 and BT plus 1 is a function of this A, B and the input. That means the next state, this is a Mealy machine, right? This Mealy machine depends on the present state and the inputs. So here the next state, this next state is function of present state A, B and the input X. It is what it is written here. Okay, so flip flop next output, so the AT plus 1 and BT plus 1. Already I told here, next state means output, next output of a flip flop. Present state means present out of a flip flop. So next flip flop output, flip flop next output, this AT plus 1 and BT plus 1, and it is a function of present state A, B and X. Okay, so here AT plus 1, BT plus 1 gives next state. Okay, and this is my output to Y. So here AT plus 1 is function of ABX, so it is a sum of 1, 2, 4, 7. See, AT plus 1, AT plus 1, this is where we are getting 1, then it is 1, then it is 1, then it is 1. So you have to use this K-map to solve this one. And if you solve this one, then what we are getting here, AT plus 1 equal to sum of 1, 2, 4, 7. This function is see, always remember this AT plus 1 is independent of clock. Means this 1, 2, 4, 7, this data must be present at the input of flip flop. See, this is my, let's say this is my flip flop, and this is A and this is A bar. Always remember the output of flip flop is called present state. This is AT, and input to a flip flop is called next state. This is AT plus 1. Okay, so what we have to remember here is output of a flip flop is present state, and that is AT, and input to a flip flop is next state. This is AT plus 1. So whatever we get here, whatever data we have here, this AT plus 1, and what is the data here? AT plus 1 is sum of 1, 2, 4, 7. If you solve this one using K-map, then this is the logic we are getting, AT plus 1. And this BT plus 1 is function of 2, 3, 5, 7. See, BT plus 1, here we are getting 1, 1, here we are getting 1, 1. You sum all these things. Okay, then BT plus 1 is 2, 3, 5, 7. This is the logic. And this output 1 we are getting here, this one and this one. If you solve this K-map, then what we are getting, Y equal to AB plus AX. Okay, this AT plus 1 and BT plus 1, this logic is present here. Then this logic is present to the input of another flip flop, that is output is B and it is B dex, and this is my clock. Okay, so this data is independent. These are analog circuit, right? This is analog circuit, this is also analog circuit. So this data, the data that present here at the next state, it is independent of clock. Okay, so this data must be present at the input of flip flop A. Input of flip flop A means here A. Before the clock comes, the data should be present here, that is next state. And when clock comes, then this data is propagated, this data is transferred or propagated to the output of a flip flop, that is present state. See, when we write the code, what we are writing here, see the code that we have written here, the verilog code, you remember this one. When the clock comes, this positive edge of clock, then next state, we write state equal to next state. State equal to next state means whatever data we have at next state, that is propagated to the state. So same thing here. So whenever the clock comes here, whatever data we have here, the next state, and that next state is decided by this logic. Here the next state is decided for this flip flop is by this logic. Okay, so whenever clock comes, this next state is propagated to this one. Whenever clock comes, this logic is propagated. This logic is propagated to this output of this B flip flop, this flip flop. This is the reason why we write this line in every this FSM verilog code. If clock comes, then state equal to next state. Okay, so when clock comes, the next state will move to this output of a flip flop state, and now the next state becomes state. You remember initially 0 0, then we are moving to 0 1. So 0 0 0 0, when we were in 0 0 state, it is moving to 0 1. So here next state is 0 0, sorry, here present state is 0 0, next state is 0 1. So it is next it will move to 1 0. So the next state becomes now present state, and this one become next state. This is the reason next state will move to state. That means the next state will become the present state. This is the meaning of this one. Okay, and the circuit for this one. Okay, this is the hardware implementation of the FSM. You remember this one? This already using the K-map we solved this one. AT plus 1 is this one, BT plus 1 is this one, and Y equal to this one, output of this FSM. Okay, then the hardware for this hardware implementation of this FSM is we have two flip flops, right? A and B. Input to this one, and input to this one, that is next state. The next state is decided by this logic, this combinational logic. So this is my X input, then A dash, B dash, A, B, all these things are there. Okay, this is a combinational circuit, combinational logic. This is the pure combinational logic, and which gives the next state at t plus 1 when current state is at t, and this is the output. This input is coming from the outside world. Okay, so these are the output here, and this is also output here. So this is present or current state. This represent the present and current state, means the output of flip flop. And then this is the output. This output here we are getting Y logic. Here we have solved Y equal to AB plus AX, and this output, it is connected to the outside world. That means it interacts with the outside world, and the logic for this one is this one. This A is this one, and this B is this one. Okay, so this is the hardware implementation of this FSM. Next one is this one. So if someone give you this kind of finite state machine, then see here 0 0 0 0 0 1. So 3 bits. The state variables are of 3 bits. 3 bits means 3 flip flops are required. Here only one input, and then this input is, see, there is no input here. Okay, for every time transition there is an input, but this transition 1 0 1 2 0 0 1 there is no input. No input means it is a don't care. There is a don't care for this input. Okay, no output variable used. Here we use output variables, state variables A and B, but in this case we do not have any state variables, right? This output variables, because there is no output. See there, it is not written like this, or it is not written like this. So there is no, what you call this, state variables, that output variables. State variables used, you use the state variables, but there is no output variables here. Okay, state variables is this one, A, B, C. Okay, but there is no output variables. Total 5 state, 1 2 3 4 5 states. 5 state means 3 bit is enough. 3 bit is enough, right? 3 bits. 3 unused states, because this is 0 0 to 1 0 1. Unused states are here. 1 0 1 means 1. This is 5. 3 then 5. So let's say it is 1 0 0. So 1 0 1 1 1 0 1 1 1 1 1. So 3 unused states. So use Moore. Better to use Moore, because here there is no, see, why to use Moore here? because here there is no output is given, yes, right? Here there is no output given, here there is no output given, so it is better to use Moore. It shoots here. Okay, one more most important here is one point is, see here, total 3 number of unused states are here. Okay, when power off, then what will happen? If when power off for the first time, let's say you go to ATM, you go to a ATM, okay, then you take out your money by entering your pin, okay, by doing all this formality, okay, but let's say initially it is not turned on, that ATM is okay, and let's say you switch on this ATM. What if it moves to a unused state? See here, total 3 number of unused states are there. So when for the first time when the machine is powered off, the machine may start off in one of the unused states. Then what will happen? We know that when this state is this one, and some input comes, then it will move to this one. Then when some input comes from, then this will move to this one. Then from there is a transition. Here there is a transition. There is a transition. There is a transition. But because of some kind of noise, let's say some electrical noise, if the machine starts in one of the unused states, then what will happen? Then machine may freeze. You remember the hanging of your, what you call this, sometime mobile device or some kind of electronics gadgets hanging, sometimes it is hanged, right? Or the machine may freeze. So what do you do in order to avoid this situation, so that your machine is not going to start in one of the unused states? We add reset. You remember this one? We extra hardware, that is using extra hardware. See here, we are using a reset, and what we are doing here, when reset equal to ones, then it will move to a known state. Here S0 is known state. Sorry, yes, S0 is a known state. So what we do here, in order to avoid that situation, we use a reset signal, reset pin. This reset pin, definitely this, if you are adding a reset pin, then definitely it is going to add extra hardware. But still to avoid this situation, we are adding a reset logic to force the machine into some known state when power off. This is the reason why every state machine, there will be a reset signal. There will be a reset signal like this. Okay, reset. This is the use of reset signal is the one that I explained. Okay, so this is one of the most important question during the interview. They may ask, okay, this question, okay, that you have to remember. Then what we are doing here, see, the next one is different encoding technique for the FSM. Okay, already we saw here, see here, state variables, we have 3 bit we have taken for ABC, the state variables. So this is called encoding technique. You remember this one, this code here, this verilog code, we have written parameter S0 equal to 0, then S1 equal to 1. So for this state variables we have taken 1 bit. For this state variables we have taken 1 bit. Okay, so that is called binary encoding. Here in this case we have taken we have 3 state variables. 3 state variables means 3 number of flip-flops. See here 3 flip-flop used for each state. So for a 5 state machine, it is a 5 state machine, right? I mean, there is a 5 number of transition. Okay, this is a 5 state machine. So for a 5 state machine, 3 bits is required, right? So 3 bits are required, means 3 number of flip-flop we have taken. So let's say first one is 0 0 0, then 0, so 0 0 0, it represents, this one is for 1 flip-flop, this is for 1 flip-flop, this is for 1 flip-flop. Okay, so 0 0 1, so this is flip-flop, this is flip-flop, this is flip-flop. Okay, so we have taken 3 number of flip-flop, and this type of technique is called binary encoding. Like this is 0 0 0, then 0 0 1, then 0 1 0, next is 0 1 1, then 1 0 0, 1 0 1, then 1 1 0, 1 1 1. This kind of encoding technique is called binary encoding technique. But there is another famous encoding technique that is used in case of this FSM. that is called one hot encoding, and it is mostly, it is mostly used in FPGA design. Okay, and it is this one encoding technique. During that VLSI interview, most of the interview, they ask this question: what is one hot encoding technique, and what is the benefit of using this one, and why it is used in FPGA design. Okay, what is one hot encoding technique is here. See here, we are using 3 number of flip flop. If it is a 5 state machine, then 3 number of flip flop. Let's say if it is a 4 state machine, then 2 number of flip flop, 0 0 0 1 1 0 1 1. But what we do here, so for every this one flip flop, for right side another flip flop. But what we do here, one hot encoding technique here, one flip flop used for each state. One flip flop is used for each state. So here I have 5 number of state machines. That means for 5 state machine, it uses 5 number of flip flop. Okay, one flip flop used for each state, that you have to remember in one hot encoding technique. So in our case, for 5 state machine, it has 5 it uses 5 number of flip flop for 5 states. So what is the difference here? Binary encoding and this one hot encoding. In binary encoding technique, we are using just 3 number of flip flop is enough. But here in our case, one hot encoding technique, here we are using 5 number of flip flop. If the number of state increases, then definitely number of flip flop also increases. Then why it is so famous, this one hot encoding technique in FPGAs, or for the FSM, why it is used one hot encoding technique? Still, even if the number of flip flop increases, this is the advantage. Here we achieve higher system clock speed. This is the one that we have to remember. Advantage is we achieve higher system clock speed, as system need not to be decoded on output side. Because here, see, let me explain this one. This time, this binary encoding technique, what we are doing? 0 0 to 1 1 1 we have, okay, for 3 bits. But in our case, this one hot encoding, what is happening for first state? Because we are using 5 number of flip flops, so only one flip flop see in one hot encoding, only one flip flop see a 1 at any time. See here, for first one, see here 0 0, then 0 0 1, then 0 0 0 1 0, then 0 1 1. But in our class, what will happen? For first state, it is not 0 0 0 0, it is 0 0 0 0 1, then 0 0 0 1 0, then 0 0 1 0 0, then this one, then this one. See here, for every state there is one flip flop here, 1, right? 1 here, 1 here, 1 here. Okay, so system need not to be, so here decoding is very easy. In this case, decoding is little bit complex for binary encoding at the output. But in our case, that means in one hot encoding case, your decoding is very easy at the output. A system need not to be decoded on output. And this logic is also so simple, because at any time only one flip flop is present here. At any time only one flip flop. Though we are using many number of flip flops, that doesn't mean that definitely it is going to take more hardware, because more number of flip flops. But another advantage here is we are using less combinational logic is required, because decoding is very easy. Or there is no need of decoding, and the logic is so simple here. So less number of combinational logic, and if less number of combinational logic is used, then definitely the system will be faster. Okay, so this is the one main advantage of using this one hot encoding technique. Okay, so here again circuit for this one hot encoding, this This is the same one, okay? Mealy. Then this is my state table. And now for 1 0, you remember this one? For 1 0, we were using two number of flip flop. If you use the binary encoding technique, see here. For 1 0, 1 0 means, acha, what is 1 0? 1 0, the state is 1 0 means this one is 1 and this one is 1 and this one is 0. That means output of this one is 1, output of this one is 0. If it is 0 0 state means out of this one is 0, output of this one is 0. If it is 0 1 means output of this flip flop is 0 and output of this flip flop is 1. Okay, so we are using two number of flip flop. If we use binary binary encoding, but if you use one hot encoding technique, then we are using only one flip flop. See here, for state 1 0, we have only one number of flip flop here. Okay, so this is the logic. This is the input circuit, and this is single flip flop. So what is happening here? This flip flop equal to 1. This flip flop equal to 1. 1 means this 1 0. 1 0. This flip flop equal to 1 means FSM is in state 1 0. This FSM is in state 1 0. 1 0 means this one. This FSM is in state 1 0. Okay. When it will be in state 1 0? This is the circuit for this one. Okay. When the state will be in FSM 1 0? If it is currently 1. If it is currently 1 means here it is written if it is currently 1. Currently 1 means it is in state 1 0. If it is in state 1 0, that means it is currently 1. That means, okay. So it is currently, this is the currently 1 means current state, present state is this one 1 0. See, this is 1 0, right? So what we have to find is when the FSM will be in 1 0. That means this one. When the next state will be 1 0. When you are in present state 1 0 and input 0 comes, right? So it is written here. This flip flop will be in state 1 when it is currently in state, it is currently 1 means it is currently, the present state is 1 0 and the input comes x equal to 0, x equal to 0, or the state will be 1 0 when present state is 0 0, present state is 0 0 means when state 0 0 1, 0 0 1 in the 0 0 1 means present state equal to 1. Okay, the present state is 0 0. So present state is 0 0 and 1 comes and x equal to 1 comes. This is how it is analyzed, how this FSM circuits, the FSM logics are analyzed. This is what I am trying to explain here. Okay, and the logic for this one, this logic for 1 0 state, the logic for 1 0 state is this one. This is the circuit diagram for, okay, and we know that for this one, for the output of this one, it depends on the state, depending on the state, and this state is, the state output is given to this AND gate, and it is also depending on the inputs. Okay, this is depending on the inputs. So this is all about this analysis of circuit and how to what you call this how to do the hardware implementation for a particular FSM, whether it is a Mealy or it is a Moore. I tried to explain all these concepts, both using this verilog code and the logic in the sense circuit level. Okay, circuit. So I hope that you all understood this FSM now very clearly, but still if you have a doubt, then you can ask me on the comment section. Okay, so thank you so much for watching.